title of my report is DEPCOMM, Graph Summarization of System Audit Logs for Attack Investigation. Causality analysis generates a dependency graph from system audit logs, which has been an important solution for attack investigation. Despite the promising early results, causality analysis often produces a large graph and is a daunting task for security analysts to inspect such a large graph. The challenges and key insights is: firstly, dependency graph is a type of heterogeneous graph. System activities are often represented as a set of process nodes that have either strong correlation with each other or data dependencies through some resource nodes. We refer to this type of closely related processes as intimate processes. Thus, to address the challenge, DEPCOMM partitions a dependency graph into process-centric communities, where each community includes a group of intimate processes and the system resources accessed by these processes. Secondly, they are often caused by less important and repetitive system activities, such as backup file updates. DEPCOMM can identify patterns of repetitive edges and compress them inside the communities. Thirdly, major system activities, such as compressing files, and attack behaviors, such as leaking data, are often represented as information flows connecting communities and referred as infopaths. DEPCOMM prioritizes infopaths that are more likely to represent major system activities and use them as the community summary. To address the challenge, we propose a framework, DEPCOMM, for summarizing the dependency graph for facilitating attack uncovery. Firstly, DEPCOMM applies causality analysis on a point of interest event to generate a dependency graph. Secondly, merges repetitive edges and filter read-only files. Thirdly, partitions a dependency graph as process-centric communities, and then compresses repetitive edges inside a community. Lastly, identifies top-ranked infopaths as graph summary. For the process-centric community detection, DEPCOMM first performs random walks on each process node to obtain walk routes. We propose hierarchical walk schemes, leverages both local neighbors and the global process lineage trees to choose the walk routes. Then, DEPCOMM computes the behavior representation for each process node P by vectorizing these walk routes. Specifically, we first make an analogy by regarding nodes in a dependency graph as words and walk routes as ordered sequences of words. DEPCOMM learns the process node representation from all walk routes containing P by skipgram, a widely used word representation learning algorithm. Next, DEPCOMM clusters process nodes based on their behavior representation. To compute the overlapping clustering for process nodes based on their behavior representations, DEPCOMM employs a soft clustering method, FCM, that outputs the membership degree of each process node in each cluster. Lastly, DEPCOMM adds the accessed resource nodes to the detected communities according to the connection with the process nodes. For the community compression, DEPCOMM processes the process-based pattern compression, namely repetitive activities that spawn same set of processes to process some resources. At the same time, DEPCOMM processes the resource-based pattern compression, namely resources that are repetitively accessed by a same set of processes. This is an example community dependency graph. DEPCOMM partitions the dependency graph to 10 communities. The complete dependency graph has 1,038 nodes and 4,039 edges. Red dashed frames are the communities with attack-related events. Blue dashed frames are the communities with only normal events. Blue nodes represent nodes that belong to multiple communities. After compression, the number of edges of the community seed 9 decreases to 33 from 108, about 69.4% compression rate. Similarly, the community seed 9 is compressed into 2 edges from 58 edges, about 96.5% compression rate. For the community summarization, DEPCOMM extracts the info path that is more likely to represent major system activities or attack activities. Specifically, DEPCOMM uses DFS to find longest path from input nodes to output nodes, where the input nodes represent the incoming information flow for a community, namely the target node of an inter-community edge, and the output node represents the outgoing information flow for a community, namely the source node of an inter-community edge. However, there are many info paths. It is necessary to prioritize these info paths. DEPCOMM computes the prioritization score for every info path based on 4 weighted features, including POI event, input or output type, event uniqueness, and time span. According to the assigned priority scores, we sort the info path and select the top N path as the summary, where security analysts have the flexibility to choose the value of N. This is an example summary graph. Summary for each community includes master process, time span, and top-ranked info path. The evaluation dataset includes 6 attacks performed in our test environment, deployed with system monitoring tools, and 8 attacks in the DEPCOMM dataset, where the collected dataset contains about 100 million events for 3 days, and the DEPCOMM dataset contains about 15 million events. DEPCOMM partitions the dependency graphs into 18.4 communities on average. Compared with the original dependency graphs, it is 70.7 times smaller. These results indicate that with the much smaller number of communities, it is feasible to visualize all the communities for security analysts to easily see the overview of all the related system activities. Each community size is relatively small and has 15.7 nodes on average, which greatly reduces security analysts' efforts in inspecting each community. Compared with the original dependency graphs, these results also show that the community compression is quite effective in compressing the redundant edges, reducing 216.4 redundant edges on average for each community. We compare the number of events in the top 1, top 2, and top 3 info paths for all the communities with the events identified by NODAS. Top 3 info paths of DEPCOMM have averagely 21 times less edges than NODAS. In addition, a community has 4.3 input nodes and 3.9 output nodes, forming 15.7 info paths on average. We manually inspect the top 3 info paths for each community and confirm that the top 2 info paths are sufficient to represent system activities and attack behaviors. That is, we only need to inspect 12.7% of the extracted info paths. We compare DEPCOMM with 9 state-of-the-art community detection algorithms to show the effectiveness of DEPCOMM's community detection technique. We use F1 score to evaluate the overall correspondence between the detected communities and the ground truth communities labeled by us. The results show that F1 score achieved by DEPCOMM is averagely 2.29 times higher than those achieved by the baselines. This shows that our community detection algorithm is effective to detect the process-centric communities. Furthermore, even though DEPCOMM and DeepWalk both use skipgram to learn the node representation from the walk rules, DEPCOMM outperforms DeepWalk by 1.65 times on average. This shows that DEPCOMM's hierarchical walk schemes are more effective than the random walk scheme adopted by DeepWalk, which treats each node equally. The box plots in figure show the distributions of the compression rates for the nodes and edges respectively. The number of nodes and the number of edges for a community are reduced averagely by 38.4% and 44.7% respectively, with the maximum reduction being 97.3% for the nodes and 98.9% for the edges. In addition, we verified that the info paths are not changed after compression and still preserves the semantics for the task represented by a community. This is my report. If you are interested in more details, please read my paper. Thank you for listening to me.
Sorry, I'm going to use this. Do we have questions from the audience? I do have... Sorry, maybe it's creating an echo with the other microphone. I do have a curiosity about when you do this community detection, don't you, when you evaluate it on the large data sets, don't you need some sort of manual analysis to verify that this compressed representation is actually meaningful? Sorry, I should have also checked that our authors are... Can you hear us?
Yeah, yes, we can hear you.
Should I ask the question? Should I ask the question again?
So can you hear us? Can you hear us?
Yes, yes.
Oh, yeah, okay, great, yeah. So you were asking about how we collect the ground truth, right?
Yeah, like how you, I mean, do you evaluate with some manual analysis also the quality of the communities that are detected?
Yes, yes. In fact, we actually try our best to collect a high quality ground truth data set for the communities. So we first do them like heuristic search, like using the keywords and the other find out the related process, and we manually construct those communities. To better improve our ground truth, we also invite some three independent computer system researchers who has more than 10 years research experience in this field, ask them to help us verify our ground truth, and we also revise our ground truth based on their feedback.
Okay, and do you think that this approach could be also useful for, I don't know, for example, in malware analysis or even for using community detection on actual code, or is it something more specific to the logs?
Oh, thank you for the question. Yeah, so in fact, right now we use the approaches to help understanding the provenance, attack provenance graph, and we have shown one application by integrating them with the hormones, so which would be the attack detection approaches. So the way how we integrate them is like by using their rule-based approaches, we will be able to highlight which community is attack related, which community is attack irrelevant. So then you can combine our approaches with detection technique, then we will be able to better help those detection technique to explain why this is attack related.
Oh, okay. And in the tables, when you were showing the F1 score, how you were automatically, I don't know, how you were automatically measuring it? How you were
so we construct the ground truth as I just explained, and then we measure the F1 by compare whether we detect the community as the ground truth. If like we misclassify a process into another community, we'll consider it's a false positive. Yeah. Sorry, a false negative. Yeah.
Okay. Thank you. Let me check if we have questions from the audience at home. No, it looks like we don't have more questions. So thank you very much for attending remotely and for the interesting talk and work. Thank you.
Thank you. Thank you. Yeah.